Hello to all of our dedicated followers out there, and if you're a first-time listener, welcome to the Kingdom Podcast. My name is Ashley Capuzzi, and as one of the leaders of Soluna and responsible for marketing and telling our story, I'm thrilled to have some of the best in the field discussing entrepreneurship, blockchain use cases, renewable energy innovation, and so much more on our show. We hope you enjoy this episode as much as we do. Now let's get started.
Okay, welcome to the Kingdom, and here, this is Dip, the CTO, and I'm really excited about today's episode because we're joined by one of our advisors, Timo Hanke, who is a legend in the crypto space, and this is our first remote broadcast too, which is really exciting. And so the whole purpose of this specific podcast is to start talking about what the different types of chips there are and hardware there are to mine Bitcoin and why these chips are the way they are, and kind of get started on where the industry is going. And if we have time, then we could talk about our data center at the end of that. So without further ado, again, I'm Dip, the CTO, and we have Timo, who is our advisor. And Timo, thank you for joining us, man.
Yeah, hi Dip. Thanks for the opportunity to be on your podcast.
Oh, my pleasure, man. It's really exciting to have you. Could you give us a brief history on what got you into crypto? Tell us a little bit about your background and what you're doing now, if you don't mind.
Yeah, sure. Actually, how I got into crypto, that's already been a while ago. It was in 2011, and I remember I first heard about Bitcoin and immediately caught my interest. At that time, I had been teaching cryptography at a university in Aachen, and Bitcoin was really an amazing application of cryptography, especially elliptic curves, which was quite new at that time. And then it was a brilliant combination of that with economics, and those two things really captured my fascination, so I immediately jumped into it. Since we're talking about mining, it took me a little while to get into that particular subject because there were so many other aspects that were of immediate interest to me. And that was in 2013 when I joined a startup that set out to build mining ASICs.
And it's called DFINITY, right?
Yes, that's right. DFINITY is our project, where DFINITY is a general purpose computing platform, also called the Internet Computer. So a large worldwide scalable computer that is completely trustless, completely decentralized, open to be used by anyone. A platform on which anyone can upload their code, run it, interact with it. Of course, it has a fee model built in, and it has its own native token. But it's a platform that sets out to replace, to some extent, the cloud that we know of, at least for the applications that require more trust and more security than the current cloud can provide, the centralized cloud can provide.
This is awesome. So you can create Skynet, but have no danger because it's decentralized, right? Which is exciting. You have the one massive computer, but it's completely separate, so it's safe. That's great, man. So
yeah, it's safe in the sense that the moment you upload something, then it's guaranteed to run in the way that you coded it. Right? You don't have to deal with hackers, malware, firewall setup, and all that. Once you uploaded it, you can forget about those aspects.
Oh, I'm excited, man. I'm excited to see it in action. And so, I think that one of the things that John and I always talk about is how exciting the beginning of the blockchain is, and how much we expect it to kind of take over, the way we live. And I think that part of it that's confusing to a lot of the people that we talk to that are just getting started in this space is this concept of mining and why these chips are the way they are, and what I wanted to really go through is quickly go through the different kinds of chips. You had mentioned ASICs earlier, and why these chips operate the way they do, And then how does that impact what we think is happening, right? Because whether we're building cryptocurrency miners like Bitcoin, and that's what we're doing at Soluna to start, or we're giving computing platform, computing architecture power to like a platform like DFINITY, you know, different kinds of chips are going to be optimized for those use cases, right? And I'd love to just hear your explanation on how you would describe mining to a layman, and then how you would describe the different kinds of chips and why you ultimately ended up choosing an ASIC chip. And then, you know, in a sentence or two, what is an ASIC chip?
Yeah, so then we have to take a step back and look at what mining is and what the purpose of mining is. So if we look at Bitcoin, there are several aspects, and this proof of work mining in Bitcoin fulfills several purposes all at once, but they can be looked at independently. So, for example, let's say you were the Bitcoin creator and you were to distribute this new currency to the world. Then you have to find a way to decide on who to give it to. And the way Bitcoin did this was to say that, well, we're giving out a computational puzzle, which is compute intensive, and whoever solves this puzzle gets issued a little bit of new Bitcoins. And we let the world compete for those. So there was an issuance schedule from the beginning. In the beginning, it was 50 Bitcoins every 10 minutes. And according to the predefined schedule, this has gone down to now 12.5 Bitcoins every 10 minutes. And it will continue to go down in the future. And this has worked out beautifully. People started competing with their CPUs. And of course, since the returns diminished the moment more people joined this game, people transitioned to a more efficient hardware to gain an advantage over the other people participating in this game. And naturally, this led to an evolution from starting mining on CPUs to beefing up their servers, then realizing CPUs are not enough. We have to find something faster. The natural choice was GPUs. So that's the chips and graphics cards, right? They're naturally optimized for high performance computing. And of course, you have to port the software to that. People did that. That was already about a factor of 10 faster than CPUs.
So when that person wrote the code to start doing the math or the puzzle on a graphics card, it was 10 times as fast, if I understand you correctly, than the best processors.
Correct, yes. Of course, there are huge differences between the different graphics cards as well. So people found out which card would perform better than others, and so on. All this information was shared, mostly publicly shared and discussed in forums. So to give you an idea about the time, so we're talking about the CPU phase that was from 2009 to 2010, and then the year 2011 has seen the adoption of GPU miners. Then people thought, well, what's the next step? How can we go even faster? And a choice which was still relatively easy to set up without a lot of investment was the transition to the FPGAs, field programmable gate arrays. So those are kind of programmable ASICs, or general purpose ASICs. You can program them to solve whatever puzzle you like. And that gave another about 10x improvement. So the fastest FPGA machines out there were already almost 1,000 times faster than the very early CPUs. That was in 2011, 2012. But the FPGAs actually turned out had only a very short lifetime, because soon after people realized, well, we can design ASICs, application-specific integrated circuits. So that is like going out and competing with Intel and saying we're going to design a processor like Intel does, but a specific one that only solves the puzzle that is valuable to mine Bitcoins and nothing else. And of course, this allowed to introduce massive acceleration and massive specialization and parallelization into these chips. And that created an enormous boost that's unbelievable compared to what CPUs could do. So even the relatively early ASICs are able to do what about 1 million CPUs could do.
Right. Wow. That's and as a result, Bitcoin have become harder and harder to mine, right? Because there've been so many more puzzle solvers out there, and the algorithm adapts, right, for the number of puzzle solvers there are.
Yes, exactly. There's always only one pie for which everyone competes, and the returns of this pie is divided by all the miners in the world. And yeah, you can look at a difficulty chart. So the difficulty is continuously adjusted by the Bitcoin network. As the network notices that more people join, naturally they also find more solutions. And this is the number of solutions found per time interval is something that the Bitcoin network can detect. And it has programmed into its rules that it reacts to this situation by increasing the difficulty. So the same machine that you had running before now produces less solutions per time interval.
Got it. So the difficulty is a factor that was put into the code just to counteract the knowing that computing power was going to go up. And as it goes up, the difficulty increases and corrects. Okay. So what I read about you, Timo, a little bit when I joined, and I saw that you were an advisor, and I saw that you had invented Asic Boost, and I'd love to hear from you, the man, the myth, the legend. What is Asic Boost?
Yeah, that's a very interesting topic. Of course, people have tried to optimize this algorithm that stands behind the Bitcoin puzzle, which is called the well-known hash function SHA-256, SHA-256. So people have tried to optimize the computation of that function as much as possible. So what you have to do is really calculate the SHA-256 function on random input, on ever-changing input by trial and error. Now, of course, your returns are dictated by how often can you do that in a second, and also how much energy do you spend in that process. And you're trying to optimize both metrics, speed and power consumption. And that's what people have been trying to do, starting from when they were implementing it in software, and they're still doing it while implementing it in ASICs. Now, there are, of course, a number of tricks, especially in hardware. You know, you can download for instance, design a computation pipeline where new information flows in. So the beginning of the pipeline is already working on a newer problem, whereas the end of the pipeline is spitting out the solution of an older problem that you started working on earlier. So that's, for example, a popular design. But then you can also look at what happens in this pipeline. Like, how many flip-flops are in there? Can you reduce the number of flip-flops and still achieve the same result? Or can you make those flip-flops toggle less? Because each toggle, when they switch their output line from 0 to 1, that consumes a little bit of power. Now, I've been studying this, and I've been trying to look at from a higher level, well, what can we do to the algorithm? Can we maybe use the algorithm in a slightly different way to to improve these two metrics that I mentioned. And Asic Boost is an idea in that direction. So from the point of Asic design, for the Asic designer, it must appear like a cheat, because it actually alters the input that we feed into the algorithm a little bit, and doesn't improve, let's say, for example, the pipeline in the Asic itself. So what Asic Boost, the idea behind Asic Boost is that I mentioned this input into the SHA-256 puzzle. What goes in is the Bitcoin block, that's 80 bytes. And in the Bitcoin block, in these 80 bytes, there are 4 bytes dedicated to be changed. That's called the nonce. So you're supposed to increment the nonce, try again, increment the nonce, try again, and so on. So what I said, well, let's not change the nonce. Let's keep that constant, and let's change some other value in the block header. And it turned out, if you do that, you can actually reuse across different runs of the function. You can reuse some of the information that you have computed.
That's amazing. And this has been adopted quite a bit by a lot of manufacturers. This type of this process, this method of reusing parts of the math.
Yes, by now I believe it has probably become a standard, and I believe all the new chips are doing it. Of course, I don't know about every manufacturer, but it has taken a while to find adoption. But I think by now, and especially going into the future, I assume that every chip will use it.
You know, one of the things that I want to kind of bring up, and I do want to small say that there'll be a blog article with a lot more information on these different kinds of chips that we'll publish. So if people have more questions about that, that'll be up there. But I kind of want to switch gears a little bit and get your thoughts on some things, because what's happened is it looks like once, at least for Bitcoin, let's put away the other blockchain stuff for now, but at least for Bitcoin, as a couple manufacturers started developing the ASICs, they kind of got first mover advantage, and they almost had full control of the market, right? Like Bitmain, Bitfury, and Canaan were the 3 big ones. And one of the things we were looking at when we modeled it was that these 3 makers had such leverage because they could decide when new chips were coming out. And what we're seeing now is a lot more chip makers are coming out. You know, you mentioned Intel earlier. We're hearing that Samsung is starting to make chips. There's other companies like eBang, Dragon Mint, and just a whole bunch of other smaller companies, or even big companies like GMO out of Japan, that are putting out some pretty incredible ASICs. And, you know, I was just wondering what your thoughts were of the impact, right, as these chip makers continue to make chips. And they start to compete with one another. What does that mean to the miner? What does that mean to the person who, up until probably 6 months ago, was completely held hostage by what Bitmain was offering, right? I would love to get your thoughts on that.
Yeah, I think for the miner, it's a good situation to have the choice of different chips. I think it's a very natural development. Usually markets often swing like a pendulum from a more centralized phase to a more decentralized phase. I think it was specific market conditions around the time of the year 2014, 2015, where the Bitcoin price was relatively low. Mining difficulty was still very high due to the recent market bubble in 2013, and this was a situation that many chip manufacturers to leave the market. That in turn allowed, for example, Bitmain to capture the majority of the market and be a dominant player. But it's quite natural that over time this situation changes, of course. And it's clear as we approach the lower process geometries for the chips. You know, in 2013, when the first ASICs came out, they were produced on a 110 nanometer node. And then quickly, the technology progressed to using 65 nanometer, 28 nanometer, 16, and so on. So at that time, in 2015, when the first 60 nanometer ASICs came out, that was when the Bitcoin mining industry had caught up with all the rest of the silicon industry, because 16 was the very latest, newest technology out there. So it was on par with the graphics card manufacturers like NVIDIA, and it was also on par with the latest CPUs and phone CPUs. So at that point in time, it was natural that the progression of ASICs would be slowing down a little bit. Also, the interval between the release of a new model from the same manufacturer would be getting larger, because now we couldn't catch up fast through a number of years of chip development in a very short time anymore. Now the Bitcoin mining industry was advancing at the same speed as the rest of the processor technology, which would mean you could go to a new process node every, let's say, 18 months or 2 years. So the development slowed down, and that, of course, allowed new participants to enter. And combine that with the run-up in Bitcoin price in 2017 and 2018, that, of course, brought in a number of very big players as well, who had a long history in the semiconductor industry. For example, GMO or companies related to Samsung. They are now in the mining market as well. So I believe we have a more level playing field now, and this, of course, is good news for the individual miners to have a wide choice of hardware to choose from.
Yeah, that's a really good point. And I guess, in looking at these other makers, they're starting to get into it, and they're starting to bring, like you said, technology that is on par or even better with what's happening, on other sides of chip design. It looks like when you look at mathematical functions, right, and you look at other coins, other cryptocurrencies, they follow a similar progression, right? It starts with CPU, then it eventually works its way over to a GPU port. Then maybe not, they do FPGAs now, and then they come up with ASICs, and we're seeing that even algorithms that are supposed to be ASIC resistant, there's still efficiencies to be gained by creating an ASIC. I'd love to understand how, or your thoughts on how ASIC resistant algorithms can be how an ASIC can still be created. And then also, given that this progression happens, is there some other magic chip that you see on the horizon, some other way that could dethrone the ASIC? Or do you just think ASICs will continue to get better because they're so specific as it is? So there you go, two parts. I'd love to hear your thoughts on.
ASIC resistance is not a question about Bitcoin, right? Because Bitcoin has a specific mining algorithm, and that is highly unlikely to ever change. If it did change, then people would probably not call it Bitcoin anymore, because Bitcoin is so closely connected to the SHA hashing problem. So for Bitcoin, we'll always have ASICs. Now, other blockchains have tried to distinguish themselves and have tried to replicate the proof of work mining, but with a different algorithm, and they try to make this algorithm ASIC resistant, meaning they were trying to create a problem which is most efficient to solve on a general purpose hardware such as a CPU or GPU, where an ASIC could maybe give you some advantage, but most likely the advantage would be so small that it would not be worth the effort and the capital to invest into designing an ASIC in the first place. Now, history has shown that this was mostly not successful. Many algorithms that were believed by the designers to be ASIC resistant turned out not to be ASIC resistant. It's just that the advantage of an ASIC is to a lesser degree than it had been in Bitcoin, right? When I mentioned a Bitcoin ASIC could maybe do what 1,000 or 1 million CPUs could do. For other algorithms, maybe it's only what 10 CPUs can do. But still, as the competition is so fierce, every little advantage becomes worth the one-time non-recurring cost to invest into designing this ASIC, right? And of course, as I mentioned, it's not only speed, it's also power consumption. Power consumption is the driving factor, and it's always possible if you're talking about one specific type of computation, there's always a way to specialize the hardware and make it use less power for this computation. So ASIC resistant has been a nice idea, but has not been very successful.
Oh man, we're coming up against our time. We had some other topics to chat about. Talking about one of the things that Soluna is doing, right? So as we talk about mining and crypto and Bitcoin, a lot of the headlines out there talk about how much energy it consumes, and as you mentioned earlier, there's we teased it that there's other kinds of algorithms or methods of doing decentralization, like proof of stake instead of proof of work, that could save energy. But our mindset was, well, why not just create good energy and use this as a way to fund the energy? And I think that what has been really interesting to us is dealing with this issue of generating large-scale green energy, sustainable energy power plants, and co-locating the mining equipment, because typically hardware like computers require very stable power, and green energy is not stable. And I'd love to get your thoughts on how an ASIC chip reacts to non-stable power being power cycled relative to a CPU or a GPU, or if there's any difference at all.
Yes. So an ASIC chip for Bitcoin mining usually runs under 100% load all the time without interruption. And what also distinguishes a Bitcoin mining chip is that the power density is extremely high. So the amount of power that goes through a 1 square millimeter of silicon, for example, is unimaginably high compared to what it is on basically any other type of silicon. So that brings a number of challenges when you design the chip itself, because you have to plan for how this heat is distributed and taken away. It presents a design for the package, and it presents a challenge for the package and also for the board, for the PCB. It has to deliver this power. Now, power spikes are also automatically a problem, specifically for the board and for the DC-DC converters that have to deliver the right voltage and the right current to the chip. So this altogether has made it difficult if there's a change in load. So, for example, when you turn on your ASIC, your server containing the mining ASICs, that creates a huge power spike, and so it does when you shut it down. Now, this makes it a priori not a good device to be used in a setting where you have to change the load, right? Where you have to adjust for a change in the supply of power. But over the time, of course, the technology has advanced. People have known this problem and designed for it. So certain features have been built into the chip that allow it more easily to ramp up and down, which can be pretty easily done. For example, you can slowly increase the clock rate, or you also have to see that there's massive parallelization going on inside the chip. So for example, a chip could contain 1,000 cores, and each of them working in parallel. Now, naturally, if you provide work to these cores, it takes some time to get the work into the chip. So naturally, these cores are not going to start working all at the same time. They will start working in a staggered way, which will lead to the power to increase slowly, right? So I think technology has come a long way, and nowadays it shouldn't be a big problem anymore to operate them in an environment where your supply side changes, and you can very easily adjust the draw by turning cores, turning ASICs, or turning servers up and down. That's not a problem anymore.
Timo, I want to be mindful of your time. Thank you so much for joining us and bestowing some amazing wisdom on us. We will be bothering you again to come join us again and bestow more as we get going. I'd like to continue to have a deeper technical discussion with you as we start going through some of these challenges, and just to share with the folks how we deal with them and how we think through them, and it's an honor to work with you. Thank you so much for your time, man.
Yes, absolutely, Dip. My pleasure. Happy to join anytime.
Thank you so much for your time, audience and supporters of Soluna. We're really excited to offer more and more podcasts with technical themes like this one as we keep going, and it'll be really exciting. Thanks again.